Welcome to the fourth colloquium in our special summer colloquium series on stereotyping and medical AI. My name is Els Kingma. I'm the Sowerby Professor of Philosophy and Medicine at King's College London. So I will be chairing today's seminar. So normally I announce the chair, but today we skip that part. So instead it will be my great pleasure to introduce my good friend and former colleague, Dr. Will McNeill, who's a lecturer in philosophy at the University of Southampton, and he works in the philosophy of mind, artificial intelligence, and epistemology. His talk is entitled Neural Networks and Explanatory Opacity. I've seen this talk before, or a version of it, so I'm really keen to see how it's developed. I'm sure I will like it again. So as per usual, this talk will be recorded and posted on our website and YouTube channel at the links that we're posting in the chat. Ticket holders to our colloquia will be notified once recordings become available. You can also sign up to our project's newsletter or follow us on social media, links of which have also been posted in our chats, in order to be notified once registration opens for future events. And so just to be clear, I think the talk will be recorded, but the question and answer session is not. Is that right, Winnie?
Yes, that's correct.
That's right. Sorry, and I'm also just trying to post things in the chat. Yeah,
just want to be clear about that. So it's not like people will be recorded when they're asking questions. I also want to quickly mention that our next colloquium is in fact taking place in just a week's time, and a link to register for that has been posted in the chat. That will be a special legal themed panel discussion that we've jointly organized with the, I don't know how to pronounce this, Yeo Chong Lei Center for Politics, Philosophy and Law, or the YTL Center, it's a bit easier. And in particular, Dr. Jonathan Gingerich, who is lecturer in the philosophy of law and the YTL Center, will lead the panel discussions. Other panelists include our very own Professor David Papineau from King's Philosophy, as well as Professor Paul G. Gardner. So over to our talk for today. As per usual, Dr. McNeill's talk will last between 45 to 60 minutes, and then we'll take a 5-minute screen break after the talk and before the Q&A, which I will be chairing. So without any further ado then, please over to Will.
Well, thank you very much, Elslyn and Winnie, for inviting me and organising this, and indeed the series in general. I'm very honoured to have been asked. I'd also like to thank them for the way in which the questions for this colloquia have been set up. I think setting things up as they've done in terms of the nature and role of stereotypes in relation to artificial intelligence, particularly in relation to medical AI, I think is a really nice way of doing things. And just to sort of set the scene, I've been spending quite a lot of time thinking about those questions in the really nice way that they've been formulated, but not enough time actually integrating them into my talk. So I apologize in advance. So thank you, firstly, and also apologies that I haven't managed to integrate some of the really nice ways in which you've set up the sort of problem space here into my talk. I am sort of partly for that reason, hoping that we can have as long to discuss things as possible. So I'm very happy if people want to cut me off after 45 minutes, if I am still whittering on. So just a little bit of background. So my background is in the philosophy of perception, and the sense or extent to which there might be opacity with regard to explanations of the nature of human perception. And that's what led me to thinking about artificial neural networks, because these seem like they're an interesting, very simplified model in some senses of human perception, and some of the ways in which that might be true, and of course some of the reasons why there are limits to that might hopefully come out during this paper. But for now, I want to argue for sort of two big things, or at least there's two big things on my agenda for this afternoon. And the first one is to try and understand the following claim. And the claim is that artificial deep neural networks are explanatorily opaque. And this is a claim that you find made not only by people like me, who are lay people with regard to building artificial neural networks, but also by the designers of these systems themselves. They will say things like these systems are uninterpretable, or they are inexplicable, or indeed they're explanatory opaque. And one of the things I want to do is to try and make sense of what can be meant by that. And hopefully in doing so, we'll get a bit more of a sense by the end of when things are going to be explanatorily opaque in this domain, and what that really means for us as users of these systems. So that's going to be the main point of the talk, is just to try and make sense of explanatory opacity, what that could possibly mean in this domain. But I also then want to end by just thinking about the kind of implications that explanatory opacity might have for stakeholders. And in a way, this is going to be much more of a series of question marks, because I think that there might well be specific reasons for optimism, and perhaps specific reasons for some kinds of pessimism with regards to explanatory opacity, specifically within the medical AI domain. And it'd be really interesting to hear people's thoughts on that. So let's begin. So the way to do this, or the way I'm going to start, is just by trying to break down this claim a little bit more. The first thing we need to do is to understand something, and it's just going to be a very little, about what an artificial deep neural network is, what counts as such a thing, and then we'll think about opacity and the kind of explanation that might be at work in. So what is an artificial deep neural network? Well, it is a network of functional nodes where we think of there as being an input layer. This is taking things like, bitmaps, pixel, information from pixels from bitmaps, for example. We think of there as being an output layer, which is outputting various things that then get interpreted by the user. And then we've got these hidden layers where you have functional nodes which are sensitive to the layer before them, to the activation function of the nodes before them, and which in turn activate and then have an impact on the activation of nodes further downstream in the system. And what counts as a deep neural network is really just a network with more than one hidden layer. That's the definition. But these days we find deep neural networks with 6, 10, hundreds of hidden layers. And the network that you're looking at, it really is a toy example. If you think about the input layer in a functioning deep neural network, this is going to be many thousands of nodes. And then if you think about the number of connections between those nodes and the nodes that one needs in the hidden layers, you're starting very quickly to talk about there being millions of these nodes and many, many connections, of course, between those nodes. So these are very complicated systems. And one of the things that's interesting about them is that they are trained. So the way in which they get to provide us with interesting outputs, given their inputs, is that they are just provided with information that we think is relevant. And then depending on the accuracy and the nature of the outputs, we can then back propagate in various ways to try and carve a system which generates more interesting outputs. So just to take the toy example that I will use, if we are thinking about bitmap images, they may be of cats, or they may be of other animals, or indeed things which are not animals at all. What you're looking for is, in my toy example, is a system which, whenever there is an input which is a representation of the cat, the output is going to be interpretable as representing the existence of the cat in the image. And how do you get there? You train it, it gets better and better. The activation weights of these various nodes change, and after many iterations of that kind of training, you get very accurate outputs. One thing to note, so this is, I've given you a toy example and an even more toyish image. There are lots of different kinds of deep neural networks. So there are convolutional neural networks and recurrent neural networks. There are various, obviously there can be differences in the number of nodes, the number of layers that get used, in the way in which the activation weights are, so the sort of schema of the activation weights, the training function, so how the output is used to affect changes in the activation functions of the nodes, and different training tools that get used. Right, there are tools of art here that practitioners use, for instance, dropping out random nodes at a particular point during training to try and stop the system from overfitting and only being good at spotting cats in the training data rather than being generalizable to further bits of data. So there's an awful lot of complexity hidden in the very toy way in which I'm talking, but hopefully you've got an idea of what a neural net is and how roughly it works. So let's think a little bit about what people say about these deep neural networks. So this is Demis Hassabis, who's the founder of Google DeepMind, who has put these nets to use in various very exciting and fascinating ways. And he said, and he hasn't changed his mind on this as far as I know, he said, look, we roughly know what's going on, right? We roughly know what the system is doing, but we can't specifically say this bit of code, these nodes, this collection of nodes, this layer or whatever is doing this particular thing. And he adds, for safety critical systems, so one might imagine many of the systems in the medical sphere, you really would want to know why a decision was made. And we take it that the answer must be, look, we want to know which bits of code are doing what. That would be an answer to the question of why a particular decision is being made. And we don't have that. That's the thing. Here's the Lord's report on artificial intelligence from 2018. There was a big cross-party review, which ended up in this big report, which has been widely used and referenced. And they say, we believe it's not acceptable to deploy an artificial intelligence system which could have a substantial impact on an individual's life unless it can generate a full and satisfactory explanation for the decisions it will take. In cases such as deep neural networks, where they say it's not yet possible to generate thorough explanations for the decisions that are made, this may mean delaying their deployment for particular uses until alternative solutions are found. So here's what people are saying about the explanatory opacity of artificial neural networks. But what they're saying is compatible with various interpretations. So let's think a little bit more about opacity. Well, we don't get very far by thinking about opacity on its own, I suggest, right? Because all one means when one says that a system is opaque is to say that its functions are not apparent. Right? In other words, that it's in a black box. And we know that there's lots of different senses in which a system might be in a black box. Right? You might have just put it in a black box. In other words, you might just be not thinking about it. But it might be that it's a black box to you, but not to your neighbor in the programming office. Right? So it might be a black box, it might be opaque, just relative to your position within the processes which are going on, but perfectly transparent to other people. So to say that a system is opaque on its own is not to say very much. Really, what we need to think about is what explanations we're looking for, and indeed the nature of explanation itself. So let's think about that. Now, when philosophers start talking about explanation, there are still very live and very deep debates about whether, for example, explanations are ontic or epistemic, right? Whether they're out there in the world or whether they're representations of the world, right? Whether or to what extent subjectivity is relevant here, whether or to what extent they're relative to background knowledge or interests, and so on. Now, I know that I'm going to tread on the toes of lots of those really deep philosophical questions about explanation. But what I want you to focus on are some slightly different questions about the nature of explanation. And these are questions that we can ask when we start thinking about the contrasts between what it is to explain, or what indeed explanatory opacity might be, and other things which are nearby. So what I want you to do, or what I want you to agree with me, is that there is a distinction between genuine explanatory opacity and mere explanatory obscurity, that there's an important distinction between a genuine explanation of something and a simple empirical generalization, or simple true empirical generalization of that thing. And that there are different kinds of explanations that we want, depending on whether we're interested in types or tokens, whether our explananda, the things that we want to explain, are types, or whether they're tokens. So let's think first about explanatory obscurity and the difference between this and opacity. So there are lots of wonderful examples of things going wrong in engineering, but here's the example I'm going to use. In 1996, the European Space Agency was testing its new Ariane rocket. And this was the first test flight of that rocket. And the rocket very, very quickly became unstable and had to destroy itself. So it just lasted 37 seconds and blew up. So that was a very expensive accident. And there's an obvious sense in which the problem was opaque to the rocket's designers. So when this thing blew up, they could not explain why it blew up. They didn't predict its blowing up. And so in those clear ways, there was opacity here about why the system failed. But I want to suggest that that's quite a cheap sense of explanatory opacity. For one thing, there's a sense in which the systems here, even though the systems are all, completely classical computational systems, they're all in one sense transparent. The systems here, might have been in a black box for various people. In fact, the system that was at fault was a system that was just inherited from a previous Ariane rocket. And in that sense, people probably hadn't thought about it very much, hadn't inspected it. In that sense, it's sort of opaque to them. But this sense of opacity is just way too cheap, right? If the claim that artificial deep neural networks are explanatory or opaque is just the claim that they're like the systems on the Ariane rocket, then it doesn't look like there's anything particularly interesting about that, or anything specifically interesting, at least, that puts deep neural networks apart from any other complicated engineering system. So what went wrong with the Ariane 5 rocket was just that there was a conversion error. So there were some trajectory values that were coming in 64-bit floating point, and they were being translated into a 16-bit integer for the purposes of other systems on the rocket, and that just led to a rounding error. They just couldn't compress the information from that 64-bit floating point trajectory value into the 16-bit integer. There was a rounding error, which then got iterated and made this rocket go off course. So as soon as we find that out, right, there's nothing sort of deeply opaque there, right? And all of the representations that are relevant to explaining why the rocket blew up are perfectly transparent in the sense that they're easily accessible to us, and that once we've accessed this conversion system, okay, and thought about its role within the system, we thereby have an explanation for what went wrong in this particular case. Now, notice that what we're doing when we're explaining the explosion of this rocket by talking about this conversion error is talking about a particular token. Okay, so there's a particular explosion at a particular time, and we're interested in explaining why that happened, and we can point to this conversion error. Notice though that generalizes, because any rocket with this particular system that is launched at this particular time and so on, or this particular kind of time, or any type of rocket that's exactly like this is going to veer off course and have to explode itself for the exact same reason that this rocket does. So even though we've identified like a token explanation, an explanation of a token event, we can generalize that to a type. And luckily, of course, they didn't need to keep building these rockets to see whether that was true. We can just see by looking at that explanation that that is going to show us why these rockets will reliably blow up very quickly after launch. Another thing, oh, by the way, there's just this one. I shouldn't really. This is a complete side note, okay? But there's this amazing fact, which is that the main guns on U.S. Navy ships were targeted with analog computers until the mid-2000s to avoid this kind of rounding error problem. And when I say analog computers, I mean camshafts and gears and transmissions. So the US Navy thought that it was less dangerous to have the mechanical problems of wear and tear on gears and camshafts than to have the possibility of rounding errors on very complicated calculations. Until the mid-2000s, computers, I mean, certainly people of my age think the computers were quite impressive by the mid-2000s. Just a little side note. Okay, the other thing that I want you to focus on about explanations. So we've thought about the difference between like something that's genuinely opaque, right? You look at the system and you still don't know, you still can't explain why it does what it does. And systems which are just explanatory or obscure, right? They're just complicated and you might not have noticed what was there all along to be discovered. We've also thought about the difference between type and token explanander and how that makes a difference to explanations, or in the case of the Ariane type rocket, we can move between them. The other thing I wanted to note is the difference, or I want you to agree with me, it'd be interesting to see whether people do, is the difference between a genuine explanation and merely an empirical generalization. So take something like the Boyle-Charles ideal gas law. This captures some regularities between temperature, volume, and pressure in gases, at least until those pressures and temperatures become very extreme. So just at normal, relatively normal temperatures and pressures. The Boyle-Charles gas law captures some regularities, ways in which those things relate to each other. But I take it, and I want you to agree with me, that the Boyle-Charles gas law doesn't actually explain why gases behave in those ways, or why we find regularities in, when we change the pressure, we find regularities in either how the volume or the temperature changes in a gas. If we want to explain those things, we don't stop with the Boyle-Charles gas law, which looks like it might be a sort of readily true empirical generalization which captures those regularities. Rather, we're going to have to look to something that looks much more like basic physics if we really want to understand why those regularities hold. In other words, if we want a genuine explanation of why temperature, volume, and pressure in the gas are related in the way that we find. So we've got these three things to do with explanation, and we've got a way of sort of finding that there's a cheap version of opacity, and I take it that when Demis Hassabis says that there's a sense in which his systems are opaque, he's not talking about that cheap version. But of course, that should be really, really puzzling. Okay, so, you know, I come from thinking about natural neural networks and perception, where we really don't know very much about how these systems work. You know, we're still, neuroscientists are still doing lots of heavy work and really interesting work in trying to find out about the system itself, let alone how it does what we know that it does. But deep neural network designers, having one perfectly acceptable sense, I think, complete knowledge of their systems, right? They know all of the internal mathematical or functional architecture of their systems. For any node or group of nodes at any point in the training or implementation of these systems, they can perfectly inspect, analyze, and describe what the structures are which are realizing the system's behavior. And of course, they know all of the, at least all of the training stimuli for the system. And if they're keeping good records, they'll know all of the stimuli that the system has, even after it's been trained. And of course, they know what their training algorithms were. And they know why they chose those training algorithms and the various other design decisions that they had to make. So I think we should be genuinely puzzled when Demis Esava says that he doesn't know how these systems work, because there's a perfectly obvious sense in which we know everything about how these systems work in a way that we could never even hope to know how natural neural networks work in the same way, or a particular natural network, my perceptual systems, for instance, work. So one reaction to this, I think, is just to suggest that actually it must be the sort of cheap notion of explanatory opacity which is the issue, right? Perhaps what this means is that the system is opaque in practice, right? In other words, it's in practice a black box because they don't do all of the inspection as the Ariane 5 rocket designers didn't do all of the inspection of the systems that they inherited from the Ariane 4. Or he might mean that it's opaque to the layperson because the layperson just isn't going to understand all those sigmoidal functions and the various complexities of the algorithms which are employed and which are perfectly transparent for someone like Demis Esava. And there are various quotations you can find, you know, just as you can find lots of quotations from artificial neural network designers about how opaque and uninterpretable their systems are, you can find lots of optimistic claims as well, which might make you think that it's this cheap version of opacity which is really the issue. So you get people talking about how they can really understand what's going on in their systems. They can create saliency maps, so you find what areas of the bitmap are doing most of the causal work or creating most of the sort of causal activity in the system, which leads to its outputs. You can do various dimension reduction, clever dimension reduction things. And you also often, especially in perceptual systems, find people talking, as they do about natural neural networks, of hierarchical representation structures. So they say, look, what this system is doing is it's starting off with these very low-level representations, just the bitmap images, and then at each layer, it's getting towards the more abstract representation of the image before it, until finally it delivers you, as it were, that most abstract of representations, the high-level feature that it finds, the being a cat, or whatever exactly it is. So you find people talking in this optimistic way. But I don't think that that is actually what designers mean themselves when they say that the system is explanatory or opaque. I don't think they mean, look, actually, we've got all of these clever ways of explaining what's going on. It's just that you wouldn't understand them or we don't bother to do them for the most part. Okay. I think that actually we've got good reason philosophically for thinking that access to all that information, that complete knowledge of the implementation of the model, of the implementation of these systems, does not amount to or imply or give you automatic access to what we consider to be an explanation of the deep neural network's behavior. Okay, and that's what I think is the really interesting take-home message. And I'm going to try and give you three, I'm going to do this quite briefly, I'm going to try and give you three reasons for thinking this. These go from the more empirical to the more abstract and theoretical. So I'm going to talk about a particular paper that came actually from the DeepMind group concerning node non-selectivity. I'm going to talk about what's a great paper by DeWitt et al. Called the information problem. And I'm going to talk then in much more abstract terms about what I'll call the mapping. And by the end of this, I hope that you'll get a real sense that there is genuine room for genuine explanatory opacity, something more than just explanatory obscurity when it comes to deep neural networks. The question is going to be why. So let's think first about this more empirical and specific reason for pessimism about finding explanations in deep networks, finding explanations for why deep networks manifest the behavior they actually manifest. So in a network, we can say that a node or a system of nodes is selective of some distal feature, so a feature in the environment, like cat or representation of cat, if it tends to fire when and only when that distal feature is around. So when and only when there are cats, for example. When and only when there are representations of cats, of course, because we're talking just about pictures. And a network is said to generalize if it reliably outputs correctly. So if it reliably outputs F when and only when F is around, in response to novel inputs, in other words, inputs that it hadn't been trained on. Now, what Morkos et al. Found, and this was a very significant finding statistically, is that there's an inverse correlation between node selectivity and generalizability in deep neural networks. Okay, so the more selective your nodes or systems of nodes are, so in other words, when you inspect the trained system and you can find nodes or systems of nodes that are selective to particular distal features within the hidden layers of the system turns out to be less generalizable. In other words, it gives you less reliable outputs on data that it is not trained on. In other words, it's overfitted. Okay, it's overfitted to its training data when you can find aspects of those hidden layers which are selective to particular distal features. Now, what I take from that is that the more inspectable, the more decomposable these neural networks are, at least on these high-level perception training tasks, the less good they are. Okay? They're less generalizable, they're less able to find cats in data that they haven't been trained on. So in other words, the more intuitively mappable, right, the more intuitively we can find representations within the hidden layers of the system, the less well the system works. Okay? Inverse correlation between finding neat representations within the system and the system actually performing the job that you want it to do. So the more of a mess the system is, the better it does at giving you the right output. I now want you to think about a slightly more abstract question, which is, what really is the information, or how can we find out what the information is that the system is dealing with? Right? So remember that we've got this sort of optimistic talk about hierarchical layers of representation. And of course, we know that there are hierarchical layers in a deep neural network because it is layered in a hierarchical way. The question is, whether that's really helping us to explain the output of the system. The previous slide was meant to be a reason for pessimism. This slide is also meant to get you to be concerned with that claim. So notice first that we can't read off higher level representational structures in a deep neural network. Okay, that's something that's different between this kind of network and the systems on the Ariane 5 rocket. Right? On the Ariane 5 rocket, what you inspect is the program of the system, and when you inspect the program of the system, what you find are representations. Okay? And you find that there was a representation that was encoded in 64 bits that was then compressed into 16 bits, and that's where you find the problem. But we don't find that when we look at a deep neural network. Of course, we do find some things that we can count as being representations, but they're what one might call proximal representations. So you can think of a node as representing the state of the layer upstream from it, right? Or you can interpret it such that you can count it as being a representation of the state of the layer, or at least the connected nodes in the layer upstream from it. And of course, when we inspect the system, we also find mathematical representations because we're programming this with sigmoidal functions or whatever it is, right, that we can discover. But we're not finding any representations that link us directly to the distal image, right, which is the image that we're interested in, and the image that we're meant to be classifying and that the output is being weighted against. So one thing that's interesting now is, one thing that's interesting is that now this is a job of modeling and interpreting in a way that it's not when we're thinking about classical computing. Classical computing, we can just treat the program that we find as the stuff that we're interested in, and there's no move then to try and model or interpret or discover what these representations really are. That's not the case with deep neural network. And of course, as soon as there is that question, as soon as there's that move to be made, there are some really deep and fundamental problems with how to make the move, with how to model what kinds of representations there are and where we find those representations in the system. Just as a couple of examples, because I'm not going to focus on this too much in this particular talk, but just as a couple of examples, right? It might be, at least in a dynamic system, so a system that's taking moving images, right? It might be the rate at which particular nodes fire rather than the peak that they reach in their firing, which is carrying information. Or it might be the peak that they reach in their firing, or the threshold below which they fail to fire. Okay? Those are all different possibilities for how we think of the representations that's being embodied in systems, and thus what kinds of representations we're going to be interested in. And notice, so I talked a little bit about saliency maps, which are used and sometimes to interesting effect when you're trying to understand these deep neural networks, or at least make them better, is that a lack of activation of a particular node or system of nodes at a layer has as much causal influence on the state of the nodes at the next layer as do the activated nodes. Okay, so if what we're doing in creating a saliency map is just looking at where there's lots of activation in the system, where there's lots of sort of causal oomph going on, then that might not be capturing the way in which information is being conduited through the system, because a lack of firing is going to be just as important for how the nodes at a particular layer fire as the firing of nodes at a particular stage. So it's just not obvious where we're going to find these higher level representations, these interesting representations that get us stuck onto the distal representation, or how we would decide when it was the case that we had actually managed to find them. Okay, Now I'm going to talk at an even more abstract level, just about what I call the mapping problem. And the mapping problem gets us to stop thinking about the system itself and the structure of the system itself, and just think about the problem space here. Right? What is the system designed to do? The system, let's say, in my toy example, is an animal recognition engine. Right? Let's see, it's designed to decide whether there's an animal, decide whether the animal is a cat, or in a much more complex system, which animal is being displayed. Well, that is a serious problem for a system, okay, for any system, including us, because it's just not obvious how the low-level proximal information that you receive in any way maps onto the question of whether a representation has this high-level property of being a representation of a cat or being a cat itself. Okay, so think of these different cats, right? Here's a very sort of archetypal, stereotypical picture of a cat in some ways, right? We've got two pointy ears, we've got that sort of triangular nose going down to the mouth with little teeth, we've got the eyes and everything, so there's something nice and stereotypical about this as an image of a cat. But the system has got to also identify this second image of the cat. There's no color invariance across these two images. I guess we have got that sort of triangular nose, and we've got two eyes, but the eyes are of different shapes, they're of different colors. The pupils are of different shapes as well, or at least discernibly they look or appear different, presenting different bitmaps to us. And then even when we think about the triangle, right, well, here's an image which is obviously a cat, where the sort of classic stereotypical nose triangle down to the mouth is obscured. And it's actually if you think about the bitmaps here, there's pretty much nothing in common between these images. And of course, I can just keep presenting images that I want this system to be able to be reliable over, such that there's going to be an indefinite number of images, which all count as being images of cats, which this system should be able to correctly classify. And of course, the natural equivalent of this system, you or I, we could, in theory, I take it, classify for an indefinite number of images, whether or not those images are of cats. Okay, so there's indefinite number of bitmaps which are going to be part of the causal chain of a system that allows us to classify cats. And for anything that you find that you think is going to be a stereotype of a cat, I bet that I can find you an image which is obviously of a cat to you, and of course to an excellent cat classifying deep neural network, but which doesn't have that stereotypical low-level feature, or doesn't display that stereotypical low-level feature in the bitmap. Okay, so we can have a cat sideways on, so we wouldn't get the two eyes. We can have a cat with closed eyes. We can have a cat from behind or above. We can have a cat in low lighting, in fog, right? And you can just see its paws. I can just keep going on forever, right? Giving you different low-level structures, which nonetheless are part of the causal chain, which is allowing you to classify these things as cats. So the problem space is this, right? There's a mapping problem. We just don't expect, I think, and I can't even imagine what it would be like. Maybe maybe it's just a failure of imagination, to think that there could be a mapping of low-level features onto the high-level feature of being a representation, or being clearly a representation of a cat, a known representation of a cat. Just because it looks like there are an indefinite number of low-level features that will do the trick, and that there's nothing which all of those images have in common. So it'd be very odd, I think, to expect there to be a nice, neat, hierarchical feature mapping explanation of how we can get cats out of this system, how we can reliably get cats out of the system over all of the indefinite images that allow us to get cats. I know I'm going to get pushback on that. I really hope that I do it. I'll talk about that. Okay, so those are my 3 reasons to try and make you think that there's some genuine explanatory opacity that we find in deep neural networks, particularly when they're being used as perception, sort of categorical perception systems, which we don't find in the Ariane rocket case, which makes this interesting and different from just the case of a very complicated system, which is quite hard to understand. So where does that leave us in terms of finding what exactly is opaque in deep neural networks, given, of course, that there's this sense in which we have complete knowledge of the network? Well, look what we can do. Okay, we can give perfectly acceptable, I think, token explanations of deep neural network behavior. You take any particular output from any particular deep neural network, and you can explain the full mechanism. You can describe every aspect of the mechanism that produced that output. Okay, now it's complicated like the Ariane rocket. Okay, but it's perfectly explicable. I mean, it's not magic. There are these various sub-algorithms which relate to each other in various ways. They have various weightings, but that's all perfectly explicable. It might not be what we wanted to be explained. Okay, and notice that that token explanatory transparency is the mirror of something which is a type explanation, which is a type proximal explanation of what's going on. Right, so these are deterministic systems that we're talking about. So every time you present a trained deep neural network with exactly the same input, then given all of the internal systems, right, so long as we bracket any sort of external damage to computer equipment or cosmic rays or whatever, but that the system will always present you with the same output. Okay, so for the same cat image, the system's always either going to present you with the claim that this is a cat or it's not a cat. And that's a type explanation. Right? We're explaining output based on the type of input, and we can point to all of the mechanisms which produce that output. And I think we've got a perfectly satisfactory explanation of the system, okay, in that sense. So that's not a problem. The other thing which I'm going to say is not a problem, even though this is a little bit optimistic, is that we can, I think, get pretty good empirical generalizations of the shape of these systems. So the parameters within which the system is going to be good at classifying animals, and parameters within which it's not. Okay, now that might be optimistic, but I'm sort of happy to be optimistic in this sense. Right? Remember that I wanted you to distinguish between a mere simply true empirical generalization or roughly true empirical generalization and a genuine explanation for what's going on. So one of the things that we do with deep neural networks is we test them. Okay, and by testing them, we find that there are limits to the domain within which they're reliable. We find, as it were, the shape of the reliability of the system. And that's a really interesting thing to find. It's a little bit like finding the relationships between pressure, temperature, volume, and gas. But what that doesn't do in its own right is to explain why the system is doing what it does. Okay? And that is what we're missing, I suggest, with deep neural networks. So what we don't have is what I'm going to call, so sometimes I call these normative explanations, and I thought, God, that's such a dangerous thing to call them. And I don't think I need to. I'm going to call them output type explanations. Okay, so the question that Demis Hassabis thinks that he can't answer is specifically this question. Okay, and this is compatible with having complete knowledge of the internal systems that he's created. It's the question of how within, perhaps certain parameters even, the system outputs cat given a distal stimulus cat. That's the question that we're interested in, because of course that's the question of why the system is reliable. Like, what makes it true that the system has the reliability profile that our exhaustive testing and careful inspection has discovered that the system has? So there's lots of green on this page, which is grounds for optimism about the kinds of things we can say about deep neural network systems. But the crucial thing that it looks like we can't answer is this deeper question about why the system is reliable. Now, transport yourself back. I think I'm running out of time. Transport yourself back to my thought about the Boyle-Charles gas law. The Boyle-Charles gas law presents you with a regularity, which is roughly correct. So it's a sort of roughly true empirical generalization. But in order to get a genuine explanation, you need to find something much deeper in physics that's going to tell you why those regularities hold, why the gas law is correct and roughly correct in the ways that it is. And I suggest that what we need to do with deep neural networks is also to stop thinking about the precise structure of the network itself, because as we've seen, that's perfectly transparent. And indeed, the explanations for lots of interesting explananda that we might want answered. What we need to do instead is to think about the problem of space. So there are domains where we're interested in high-level environmental features. So perhaps that's schizophrenia, perhaps that's whether or not something is a cat, or whether or not something is a representation of a cat. Where either, like sort of minimally and weakly, we don't know what the mapping is that there might be between the higher level environmental features that we find and lower level or proximal features. So proximal features, input features of the system, or lower level features that are directly causally responsible for those proximal features. Or more strongly, where we have good reason to think that we're just not going to find any such map, where the higher level feature that we're interested in is weakly emergent. And I mean that in a way which metaphysically I hope is relatively unproblematic. There are some good definitions of weak emergence kicking around, which we can talk about in questions. So as I was preparing for this, I found an absolutely brilliant paper by Emily Sullivan, where she talks about something quite similar. So she says, look, there's a sense in which a deep neural network is a black box, but that's not actually the thing which is problematic, right? The thing which creates explanatory opacity. But the problem, when we find it, is a problem of what she calls link uncertainty. So it's the uncertainty that we might have between what the model is doing and what we're really interested in out there in the world. Now, I just want to take that one step further. So this is an epistemic question, it's a link uncertainty question. But when we think about the features that we're interested in, often these are just features where we have, I think, good reason to think that we're just not going to find a map between the high-level feature we're interested in and any low-level features in the environment. And these are situations precisely where we find ourselves using deep neural networks. And it's because, like our own natural perceptual systems, these seem to be ways of overcoming them. So when we think about the difficulty in decomposing those systems, of finding inner representations or structures of representations, of finding specific bits of code, as Dennis Hassabis put it, that do particular things for the system, I suggest that that is a reflection of something deeper, which is the nature of the problem space that we are putting these deep neural networks to. So the way that I want to put this, and this is, so I wish I could have put this more into a neat way of talking about stereotypes, because as I said at the beginning, I really like this way of thinking about the problem. But look, the best high-level feature trackers are precisely those trackers which get beyond the stereotypes. Now think about what a stereotype is. It's just an association between two properties. Or so a stereotypical X is an X which has two properties that we take rightly or wrongly to be associated with each other. Okay, so it's a map between one property and another property. And what makes perception so interesting, and what makes expertise so interesting if we think about the medical realm is that an expert goes beyond that neat sort of definitional mapping, you know, find growth that looks like this, output melanoma, right? And can start judging in much more complex and subtle and sophisticated ways over an ever increasing difference in low-level inputs that there might be, for instance, a melanoma, or in my toy example, there might be a cat. So what we want these systems for is precisely to overcome stereotypes, where when you think about stereotypes, what a stereotype is it's a way, rightly or wrongly, of mapping between one property that you found and another property that you're interested in. So I will leave you with this. This is a wonderful image, and we've got to be a little bit suspicious of this image, I think. So when you read the paper, it's not actually clear how they can judge in this kind of way what explainability really is. But there's something nice about this, right? Which is that it looks like for high-level feature recognition tasks, at least, there is an inverse correlation between how explainable your system is. So that is how easy it is to find the reasons why the system is reliable in the ways that you found that it is, and how accurate that system is. And what we find is that deep neural nets are incredibly accurate and very opaque in the sense that I've tried to identify. I don't think that's a coincidence. I think this is because what deep neural networks are doing is finding without mapping, so finding high-level features without having to map them onto lower-level properties. And that's what we do in natural perception. So I will leave you with this image because I think I've been going on for ages. Much rather have other people talk.
Thank you very much for that, Will.